Okay, welcome back to Calculus. In section 9.3, we're going to turn our attention to finding some analytic solutions to differential equations that are so-called separable. So in 9.1, we kind of talked about what the solution to a differential equation was. And in the event that you can isolate the derivative in terms of the input variable x, is what we've been denoting it, then you can just solve differential equations by integrating them. But other than that, we just looked at either graphical, qualitative things like direction fields to understand the nature of solutions of differential equations, or we found some numerical methods, Euler's method, but we haven't really solved any differential equations analytically. So today I want to show you how to solve just first order differential equations that are so-called separable. I want to tell you what a separable equation is, give you a technique to find the general solution to them. If we're given an initial condition, that is an initial value problem that requires separation, we'll solve some of those. And in particular, I want to do one from physics. We'll talk about Newton's law of cooling, translated into a differential equation. It turns out to be separable, and we'll solve it. Okay, so that's what's on the program. I'm going to talk fast as usual, stop the video a lot, and process this at your own pace. Okay. So let's just proceed by an example. I've got a differential equation here, dy dx is equal to x over y. So the right-hand side of this thing doesn't just have x's in it, so I can't just integrate it. But what I can do, if I treat the differentials dy dx algebraically like independent quantities, I could rewrite this differential equation as y times dy is equal to x times dx. All right, so what I've just done there is separated the variables. Okay, then I just integrate both sides. Take the antiderivative of y with respect to y and the antiderivative of x with respect to x. Okay, so that's 1/2 y squared. Over here, 1/2 x squared, and I'll add a constant. You don't have to add the constant on both sides. We can just lump them together. And then if I can, I want to try to solve that for y. So I think what I'm going to do is multiply everything here by 2. Okay, then take a square root. The square root has two solutions, a positive and a negative. So I'll put that in there. And this constant 2c, I mean, I can leave it like that, but really the spirit of is that if I had some initial condition, I'd need to determine that constant. I don't really care that it's twice some other constant. So in a lot of books, you'll just see the authors write c here. It used to puzzle me as a student, like how can 2c equal c if c is not 0? But the spirit is it's just some constant. But maybe here to be a slightly more precise, I'll give it some new name like k. So k is equal to 2c, okay? And there's my general solution. There's my general solution. There's actually two versions of it, a positive or a negative one, depending on whether y is positive or negative. Okay, so if I had some initial condition, I would use that initial condition to choose one of those two solutions. Positive, I'd take the positive. Negative, I'd take the negative. Nice. So that procedure kind of works as long as we can do this first step, as long as we can separate the variables. So let's take a look at, well, when is that the case? So a differential equation is separable, first order. I'm only talking about first order differential equations. If you can isolate the derivative dy dx and write it as a product of a function that only has x's in it and a function that only has y's in it. Or it's often very convenient to think of this product as actually a fraction. So I'll just write the f of y as 1 over something called h. So if I just make a variable substitution, f is 1 over h, then I can rewrite that differential equation in the form h of y dy is equal to, g of x dx. Okay, so we can separate the variables, separate x and y. That's why they're called separable equations. Not all equations are separable. If you can't factor the right-hand side of that equation into an expression of x times an expression of y, it's not separable. But if it is separable, then we're going to solve it the same way we just did. We'd integrate both sides. Okay, so here I don't have a specific example. I can't continue beyond this. But if I could, I would get some expression that only depends on y's and some expression that only depends on x's. Okay, so if I can solve it for y, like above, then I get an explicit solution. That's like an example 1. If not, then we get an implicit solution. Oops. Okay, if we have an initial condition, we use it to determine the value of the constant. Let's look at a couple of examples. Here I've got a differential equation. I wrote it in a form that makes it not so obvious it's separable, but if we factored, say, that y prime out of the left-hand side, okay, writing y prime as dy dx in the Leibniz notation, then multiply both sides by dx, and we've separated the equation. I'm going to write the function out in front of the differential. Multiplication order doesn't matter. And then we integrate both sides of that thing. All right. So I'm going to be a little bit lazy here and just write integral signs on that last line. The antiderivative of 2y is y squared. Antiderivative of cosine is sine y. Over here, what would we get? 6 divided by 2 is 3. X cubed, excuse me. Let me slow down a little bit here. I'm adding 1 to 2, so 6 divided by 3 is 2x cubed. And then I'll add my constant. And I can't solve that thing for y. Y is algebraically unisolable on the, you can't isolate it on the left-hand side. So I'm just going to leave it like this. It's an implicit solution. Implicit solution. All right. Let's look at a second example here. This one is an initial value problem because I've thrown in an initial condition. When x is equal to the cube root of 3, I want y to equal e. Okay, let's start by separating it. So we'll write y prime is x squared times y. Leibniz notation, dy dx is x squared times y. So 1 over y dy is x squared dx. And then we integrate both sides. Okay, antiderivative of 1 over y is log of the absolute value of y. Antiderivative of the right-hand side is 1/3 x cubed plus a constant. Okay, so if we exponentiate both sides of that, we get the absolute value of y is e to the 1/3 x cubed plus that constant. So if you want to get rid of the absolute value signs, we should write y is, well, plus or minus e to the 1/3 x cubed plus that constant, which by rules of exponents, we could write as plus or minus e to the 1/3 x cubed times e to that constant. Okay, and if I rename that constant, say e to the c, just give it a name like a, then I can write that's plus or minus a, but what I'm actually going to write is y is equal to just a times e to the 1/3 of x cubed, because I've just absorbed the sign into a. So you'll often see this. So if you're wondering, you can write the plus or minus if you want, but I don't need to, because if I put that constant out there, I'm kind of changing the name here of a again, because the second a that I wrote down there is kind of plus or minus the first one, because e to the something is never negative. But if I needed a negative coefficient out here, if I was taking the minus sign, well, then I'll just absorb it into that constant. Okay, so it's kind of the spirit of this stuff. When things are defined up to a constant, you don't have to multiplicatively, you don't have to write plus or minus it, because you can just absorb the minus sign into the constant. I need to use my condition here, which I've kind of forgotten here. We said, let me zoom out a little bit. We said that when x is equal to the cube root of 3, y is equal to e. Okay, so I'm going to try to squeeze that in there. Y is equal to e when x is the cube root of 3. Well, the cube root of 3 cubed is 3, and 1/3 times 3 is 1. So the right-hand side is also e, so that determines my constant in this case is 1. Okay, so the solution to this initial value problem is y is equal to 1 times e to the x cubed plus 3. I wanted to throw in some old ideas here. I've drawn a direction field for that differential equation. Okay, so you can kind of visualize the solutions there. And in that direction field, I highlighted our initial condition when x is the square root of, or cube root of 3, excuse me, I wanted y to be e. And then we determined that the constant a was equal to 1. Okay, so you can verify, plot on your own Desmos screen right on top of a direction field if you want to use Desmos to do that. Plot the function y equals e to the x cubed over 3, and you'll see that it lines up with that direction field. So that's how I found this solution, or it's how I plotted it rather, is I graphed on my Mathematica screen that equation, y equals x cubed over 3. That's the solution to this initial value problem. Okay, you can see that other solutions behave similarly if you chose initial conditions in that direction field. Nice. All right. So I'm talking fast here, but you can slow the video down and stop and think about this stuff. But let's talk about something from physics called Newton's law of cooling. So I'll just help you kind of check this out. So Newton's law of cooling is about an object that's being placed in an environment that has a smaller temperature than it, although it can also be Newton's law of heating if you want, but let's just stick with cooling. So what does Newton say? Newton says that if you take an object like a cup of coffee or something, you pour a nice hot cup of coffee and then you set it down on your desk in your room, your coffee's going to start cooling off, right? As you sit it on your desk. Why? Because the room is cooler than your coffee. And the energy wants to balance, heat wants to balance out. So the heat from your coffee is going to dissipate out into the room. And so the coffee is going to change temperature. Okay, so I'm going to write it here in a boring term, the object, but it's more fun to think about your coffee. Newton says that the coffee changes temperature at a rate, buzzword, right? That's a derivative, rate, that's proportional to the difference between the temperature of the coffee and the temperature of the environment, which we're just going to call the room temperature. Okay, so what is Newton saying? The Newton's saying that the bigger the difference between the two objects, the faster it will cool. It's proportional to the difference, which kind of makes sense, right? If your coffee is getting close to room temperature, it's not going to cool off as fast as it was when it was right out of the coffee maker at 212 degrees. So let's try to write down Newton's law of cooling as a differential equation. Right? There's a differential equation in that sentence because I see the word rate, right? It's telling me about the rate of something. So let's let t equal, say, time in whatever units. I'm not going to put the units here, but it would be in minutes, seconds, hours, I don't know, whatever unit of time you want to take. So we're going to take t to be time, little t to be time, and then let's let capital T, which depends on time, equal the temperature of the object at time t. All right, and then we have some other constant in here, actually two of them. Let's let, say, T sub r equal the room temperature. Okay, and all we know, and that's all we need to state this as a differential equation. So we'll just let T equal time, capital T is the temperature of the object at time t, T sub r is room temperature. So if I translated Newton's law of cooling into a differential equation, it says that the rate of change, right? So the rate of change is the derivative, dt dt. It's proportional to, that is a constant times, I'll just call the constant K, the difference between the object's temperature T and the room temperature. Okay, so that sentence that's all highlighted in yellow above as a differential equation is written compactly like that, right? The change in temperature with respect to time is proportional to the difference between the temperature and the room temperature. That's Newton's law of cooling as a differential equation. And this differential equation is separable. Let's solve it. Let's divide both sides by T minus the room temperature and multiply both sides by dt. So here I'm calling my input variable little t. And then let's integrate both sides of that. Okay, so we've separated the equation. The antiderivative of the left-hand side is a logarithm, T minus the room temperature. The antiderivative of the right-hand side is, well, K times T plus some constant. right? Let us assume that I called this Newton's law of cooling. So I'm going to make the assumption that the object is warmer than the room temperature. Okay, so that means that T minus TR is greater than or equal to 0. So these absolute value signs aren't actually doing anything. Okay, so I'm going to erase them. Exponentiating both sides, I get T minus TR is E to the KT plus C, which just like before, I'm going to write that as A times E to the KT, where what is A? Well, A is E to the C. You can just call AC again if you like. Okay, so then I've got my solution. T is A times E to the KT plus the room temperature. How would I determine that constant A? Well, if we had an initial condition, if say T of 0 is, I'm just going to call it T0, the initial temperature, when we can solve for A, let's do it. If we plug in T0 for T, plugging in 0 for A makes that E to the 0. That's a 1 plus TR. So that tells me that A is equal to the initial temperature minus the room temperature. Okay, so if we roll all of that together, we've got a nice solution to Newton's law of cooling. The temperature of this object at any time t is equal to that A, that's T0 minus TR, times E to the KT. Okay, K is the constant of proportionality, plus the room temperature. Nice. So that's the solution to Newton's law of cooling. Let's look at an example. Let's look at an example. Earlier, I was talking about coffee. My second favorite object to cool is brownies. So suppose that we take some brownies out of your oven. Notice how it's your oven, not my oven. We take them out at 350 degrees. Okay. And then 5 minutes later, so evidently we're measuring time in minutes, they've cooled to 225. Okay, let's assume that your kitchen is at 65 degrees Fahrenheit. And what I would like to do is find the temperature of those brownies at any time t. Well, I've got the formula written for that solution right above there, right? We can plug in, let's just kind of make our cast of characters over here. T sub 0, the room temperature is 65. I'm going to leave the units out here, but that's degrees Fahrenheit. Sorry, that's T sub R. That's the room temperature, 65. T sub 0 was the initial temperature. That's 350. That's what they came out of the oven at. Okay, K needs to be determined. But let's plug in what we've got so far. So I've kind of started to write this out down here. So I don't have to do the arithmetic in the video. So I'm plugging in my T sub 0 minus my T sub R. I don't know K, but I multiply that by E to the KT and then add T sub R. Well, 350 minus 65 is 285. Okay. So how do we find K? Well, to find K, we're going to use this fact that 5 minutes later, the brownies were 225, right? Because what does that fact tell me? We were given that when you plug in 5 for t, little t, the output should be 225. Okay, so if I scroll down a little bit, that's what I'm doing. If T of 5 is 225, okay, so I replace my temperature with 225 while I'm making time equal to 5. So now the only unknown number in that equation is K. This should remind you a lot of like half-life and doubling time problems that you've done before. So if I do the algebra here, I skipped the steps, but I would just subtract 65 from both sides, divide by 285, then take the logarithm and then divide by 5 to find K. And here I've written it out to an obscene number of decimal places. I want to say that if you're going to actually use these things to make any predictions, this thing is very sensitive to round off error. So don't round these values. Yeah, type them all in there, or if in your calculator, if you can just store that value and use it as a stored value. Because if you round this thing off, even to like 5 or 6 decimal places, it will prevent you from getting accuracy in answers about the temperature. So if I were going to hand type this thing in, believe it or not, I mean, I would literally try to type all of those digits. It looks like there's more than 12 digits there, but they're very sensitive to round off error. Okay, so now we can write our final function. We can write our final function. The temperature of these brownies at time t is 285 times e to that k. So I'm going to take my own advice and write 11546307. I mean, I know it seems ridiculous, but I'm just going to write this to emphasize that it's very sensitive to round off error. If you are going to round it, use at least 6 places. That's the number I multiply by t, and then I add 65. So if I plug a t value into this expression, what is it telling me? It's telling me the temperature of my brownies at time t in degrees Fahrenheit. Nice. I plotted this function. Sorry, I scrolled way down there for it, but this is a graph of t as written above. You can see it's a decaying exponential function. I should have asked you this while we were looking at this formula, but if you take the limit as time goes to infinity of t, well, in this exponential function, you have a negative exponent. So in that limit, the exponential term is going to go to 0. Physically, this makes perfect sense, that the limit is going to be room temperature. The temperature of the object, your brownies in this case, is going to approach the temperature of the room. And you can see that in this graph, right? So what I've drawn here in the graph in yellow, I don't know if I've got a good yellow matching color. Well, you can't really see that very well, but that's y equals 65. And you can see that the temperature of the brownies approaches that over time. Theoretically, according to our model, the temperature will never reach 65 degrees, but it will become arbitrarily close to it. Okay, so I'm going to end this with something that I always kind of try to sell on students. I don't know if you've ever baked brownies like out of a box. You guys are probably more sophisticated and bake them from scratch. But if you buy a box of brownies in the store, they usually tell you to put them on the counter and let them cool for an hour. And I'm going to go ahead and say that the last 20 minutes of that hour, you're kind of wasting time. It looks to me like, according to this model, by the time t gets to 40 minutes after you take the brownies out of the oven, they're at room temperature. So why not just eat them then? If you're a real baker, you probably know that there's some other chemical processes happening in there besides just cooling. So maybe that's why we should wait. But well, maybe I don't know if I should tell you this, but I never wait. I eat the brownies. So at time equals 40 minutes, I'm going to eat them. Okay. I hope that was fun and useful. Thanks for listening.